The paper that I will be presenting today is called Hierarchical Aligned Multimodal Learning for Named Entity Recognition on Tweet Posts, and it was published in AAAI 2024. I will be following this order for the presentation. And for introduction, social media platforms are becoming more and more important in information gaining, and they contain valuable information for various applications like identifying cyber attacks or natural disasters, analyzing public opinion, and mining disease outbreaks. And named entity recognition, shortened as NER, plays a key role in extracting structured information for these type of downstream tasks. But there's a problem because normally named entity recognition only considers text as input. But with the rise of multimodality in social media posts, traditional unimodal named entity recognition faces challenges. So now they focus on multimodal named entity recognition, which addresses this problem by incorporating images alongside text as input, and they improve the accuracy of information extraction. And here there's an example. Here in the figure 1A, the text says, "Baby Jasmine is dressed and ready to party." And this text input, if it was given to a unimodal named entity recognition model, it could be labeled as, Baby Jasmine could be labeled as a person, but the image here, it's helping to understand the context, and then the model can correctly label that as other entity because it's an animal. And here in the second image also, the text is talking about two sports team names, but since it's penguins and sharks, for example, they could be mislabeled without the background view of the image. So the image provides context here, and they are successfully labeled as organization because they are sports teams. And in the third image, actually, it shows that the text and also the image does not show any relevance to any entities. And we should consider this type of cases as well, because I will mention the reasons later. Existing multimodal named entity recognition methods are divided into four main streams in this paper. And the first one is they use pre-trained CNN models to encode images as global feature vectors, and they just combine the global feature vectors with the word representations to use the image information as well. And the second way of doing this type of task is they divide images into blocks, and transformers or gating mechanism model the interaction between the text and these visual regions to learn the most valuable vision-aware word representations. And the third is they first use object detection, and they extract the visual objects, and then they combine this with the text using different methods. And the last one is when they use derivative information from the images, like OCR or image captions. They use these to enrich the word representations with visual semantics. But there are some limitations of these existing methods. As I mentioned in the example for the third image, if studies assume that there is always an entity relevance from the image to, if they assume that there's always going to be entity relevance, this will cause problems because there can be times where both the text and the image are entity irrelevant. And the second limitation of the existing method is that they neglect the implicit knowledge that can be obtained from the images. And they rely more on explicit visual information without considering the object relations or the background view of images. And the third is they lack the multi-level semantic alignment. Here, since sentences are made of words and the images are made of attributes and objects, we need to consider the multi-level alignment between the two data types too. And existing approaches do not really consider this. So we could capture more better correlations between images and text if we focus on this as well. So from these limitations, they propose a new idea called hierarchical aligned multimodal learning, which is shortened as HAM learning. And the model is performed in three main stages. The first one is global and local feature extraction. For the word representations, they use a text transformer to learn the global sentence and contextual word representations. And at the same time, for the image information, they use two visual encoders. And both visual encoders capture the object-to-object relations and general scene information. But one does it from a semantic view and one does it from a spatial view. And the second stage of the model is global content alignment. They measure the text-image relevance through this stage, and then they use the relevance score to decide on which images are helpful to named entity recognition in the text. And they choose the visual representations like that. And then they integrate object level and image level features based on this score, as I said. And the last stage is they implement cross-modal interaction between word representations and the final comprehensive visual representations to find the most effective multimodal clues for decoding, and they do this iteratively. And here is all of the framework, and I will be mentioning each part now. First, to define the multimodal NER task, we will treat it as a sequence labeling task. And when there's a given input pair of text sentence, let's say X, and an image I, the goal of the multimodal named entity recognition is to detect the set of entities in X and classify them into predefined types. So we have the input sequence and the output sequence. Here, the output sequence is in standard Bio2 form. And for text encoding, each text sequence X is fed into a BERT model here, pre-trained BERT model. And here in the output of the, this is the input, and what's coming out from the BERT model is here. And the first element is the global sentence feature. And then they extract the word representations for all X, all of the input, all of the sentences. And then this H is fed into a text transformer for further encoding. And then we get the final output where the first element is the global representation of the text sequence, and the rest are for each word separately. And for vision encoding, they, as I said, they will focus on spatial encoding and also semantic encoding. But first, they first get image level and object level representations, and then the two encoders update the representations by capturing relationship between the different elements on spatial and semantic views. For global representation of the images, they use ResNet as the feature extractor, And when they get the feature map, they transform it into a one-dimensional vector by linear function, and the whole image feature vector is represented like this. And for local features of the objects, they use a faster GCNN model. It's pre-trained on the visual genome dataset, and they first perform object detection and output the representation of each object region. And here we can see how each feature representation of each object is seen. Here the L part is about the region, and the second part is about the label of the region. And for semantic encoding of the vision part, they arrange the whole image and object representations into a sequence, and then Vision Transformer, VIT, learns the contextual presentations using the interaction among them from a semantic view. And we get the input like, the output like this, output sequence. And for spatial encoding, we have to look at the object in a different way, because objects in the visual space are often scattered and irregular. So we cannot always look at them as sequences like we did in semantic encoding. So that's why they build a spatial structure graph for spatial modeling. And in here, here for each object, the location can be written like this. Xi, Yi is the center point of the object's region box, and H is the height of the box, and W is the width of the box. And then we get the initial spatial feature of an object like this, and then we get also the initial spatial feature of the whole image. And also relationship between the different objects are defined based on the distance and angle between them. Here in figure 3, you can see the relationship between two objects can be inside, cover, overlap, no relation, or one of the 8 classes here, due to based on the angle and the distance between them, as I said. And the spatial structure graph is the nodes in the graph are the objects, and the edges are the defined relations between them. And they update the node representations using RGCN with the initial spatial features. And for vertex I in the K layer of GCN, accumulating information from the neighbors can be represented like this. And they update the representation of I in K+1 layer through gate mechanism. And then they perform relevance measuring, as I mentioned. Relevance between the global text feature and global vision feature is represented as MR. Here, CR is a intermediate variable. So, and here these are weight matrices. This one represents for text and image together, and here we see for text and image separately. They calculated the relevance between the features like this, and then based on this, they do the training. But sorry, wait. Yes, the relevance score is calculated using the hyperbolic tangent function. And for intermodality learning, in figure 2, we saw that we checked the interaction between different modalities, and the interaction model has 3 parts, and all of them take the cross-modal transformer as the core encoder. To reduce the heterogeneity between text and vision, they transform the text representation before this step. And Also, they have they create the comprehensive vision feature in this stage as well. And then after they obtain the comprehensive vision feature through gate control, they refine representations of textual words, as you can see here, by introducing the fused spatial and semantic visual information. And as I said, the comprehensive vision feature is obtained by gate control. Then the comprehensive vision feature and the transformed text representation are put together through the transformer. And then we have the final multimodal text encoding H here. And then they do L iterations and find the final H encoding and use it for the multimodal named entity recognition decoding. And here they feed the final encoding H to CRF layer and get the probability of the predicted label sequence and train the model by maximizing conditional likelihood estimation for the training set. And then finally for decoding, they get the final label sequence prediction for a given text sequence. And they maximize the score to get the final predicted label sequence. And now I will be talking about the experiment details and the results. They did the experiments in two public data sets, which are Twitter 2015 and Twitter 2017. And here you can see that they have the same categories for the entities, but distribution and the size are a bit different. And also I gathered the implementation details here as well. And there are many baselines they use to compare performances. They use both unimodal and multimodal approaches as baselines. For unimodal approaches, they used BiLSTM plus CRF model and a version of this where they added character level word representations, but the word representations is learned by CNN, or in this case, the word representations are learned by LSTM. And they also do experiments with BERT and BERT plus CRF models as well. And for multimodal baselines, there are many baselines here. The first two have similar architectures where they combine the whole image feature through visual attention. And UMT is a cross-modal transformer to encode image region and text. The next two here, they add contrastive task to make text and image more consistent and assign a visual feature to assist words. And the next two, these two, they enhance the cross-modal interaction with GNN. And the next three here, these three, they use derivative knowledge, as I mentioned in the previous slides. They say they use the derivative knowledge of the images to guide the vision-aware information. And the last two here, they are attempts to perform multi-level semantic alignment at different visual levels. And here we can see the main results. The overall F1 score in both benchmarks are the highest for the proposed approach. And if we look at the general points we get from the experiment results, we see that for the unimodal approaches, BERT-based models outperform the BiLSTM-based encoders since they also have the advantage of being pre-trained. And also, we see that, of course, in general, unimodal approaches perform worse than multimodal approaches. So we can say that visual information significantly enhances the performance for multimodal named entity recognition. And We see that also here, MAF and RDC, these two, they remove the vision noise. So these two perform better than UMT, where there's more noise, because they don't consider removing the noise in this one. And this also shows that it's important to eliminate the vision noise and also evaluate the text image matching degree. And we see that ITA and the other two here, they achieve good results, but as I said, they rely on external tools like OCR models and handcrafted templates. And the proposed approach doesn't need any external tools like that. Also, we see that the proposed method outperforms the two other methods that consider the multi-level semantic interactions, the last two, because these two methods, they focus on only visual multi-levelness of the visual aspect, but the proposed method that looks at it in both modalities. And for ablation study, they check the three modules. Here by RGCN, they mean the spatial visual encoding. By VIT, they mean the semantic visual encoding, and RM is the relevance measuring. And we can see that removing any of these drops the performance. And we see that here the spatial visual encoding, when we remove it, the hidden information, the implicit information behind the image will be hard to capture. So we can explain the performance drop like that. And for relevance measuring, especially the recall drops a lot for both datasets, since here the unnecessary visual features produce noise and damage the performance. And also they did some analysis about some, first of all, they checked for different number of iterations, how the experiment results will change. And here we can see that the number of iterations increases and the performance improves. But after the third iteration, there's a drop. And they explain it as the cross-modal interaction learning gets more deep, the differences between modalities diminish, and with more iterations, we are not getting any more valuable feature extraction. And they check also for the generalization of the model. So they use the model trained on Twitter 17 dataset on Twitter 15 named entity recognition task. And they did also the opposite. And model showed strong transfer skills and adaptability. And also they used a different object detector too. They use mask RCNN, but it's also pre-trained on a different dataset, and this dataset has fewer object categories. So there's a bit of a drop in the performance, but they say that since the performance deviation is quite small, we can say that different object detectors don't change the performance of the model that much. And they also performed a case study. And in the first case, the image doesn't provide effective visual guidance information for named entity recognition. And this is important because this model is supposed to filter out the noisy visual data too, and it successfully does it. And in the second case, the detected object bare in the image helps the model for correct prediction, highlighting the importance of fine-grained semantic interaction between text and local objects. And they finished experiments like this. And for summarizing, the proposed method here is a novel hierarchical neural network, and it's trying to achieve the multimodal learning for multimodal named entity recognition. And it has three modules, as I explained: intramodality learning, image text relevance measuring, and then lastly, iteratively learning from cross-modal data for multimodal named entity recognition. And thank you for listening.